The BatchOp unit models processes that are likely to occur in a batch process tank. The BatchOp unit models reaction and crystallization. The crystallization reaction object can be created in the reaction folder and allows us to input solubility data and kinetic information. The BatchOp unit is only available in the batch process flowsheet. The BatchOp unit has 2 input material ports, 3 outlet material ports, and 1 outlet heat port. The 2 input material ports are the charge port and the continuous feed port. The charge port is a time average single inlet port that is required for any BatchOp unit and can be used to compute the amount and composition of the initial charge. The optional continuous feed port is a multi-port inlet and can be altered by specifying an operating change in the unit procedure. The 3 outlet material ports are the reactor product port, condensed phase liquid plus solid drop port, and vent product port. The reactor product port is a single outlet port through which the final pot contents are discharged that is required for any BatchOp unit. The continuous condensed phase drop port and vent product port are optional single outlet ports. The flow through the condensed phase drop port can be altered by specifying an operating change in the unit procedure. We will use the BatchOp unit in the batch process flowsheet to model the production of aspirin. Our BatchOp will have 1 charge feed stream, 1 continuous feed stream, and 1 product stream. We will model our aspirin production reaction and crystallization simultaneously in the BatchOp unit. Double-click on the charge stream to specify the acidic anhydride charge. Specify the temperature as 25 degrees Celsius, the pressure as 1 atmosphere, the flow rate as 400 kilograms per hour, and the mass fraction as 1 for acetic anhydride. Double-click on the continuous inlet stream to specify the salicylic acid feed. Specify the temperature as 25 degrees Celsius, the pressure as 1 atmosphere, and the mass fraction as 1 for salicylic acid. Specify the flow rate as 0 kg per hour for now. We will specify our salicylic acid flow rate in the unit procedures. Double-click the BatchOp unit to open its unit op form. We have 4 options for our reactor operating specification: specified temperature, specified heat duty, specified coolant temperature, and heat transfer user subroutine. The first 3 options allow us to provide specific values for our reactor. These specifications can be modified by a unit procedure. Specify the reactor operating specification as specified temperature and provide a temperature value of 25 degrees Celsius. Valid phases section allows us to specify the phases involved in the batch process. Leave the valid phases as liquid only. The model details section allows us to specify reaction, crystallization, or both. We want to model both our reaction and crystallization. The pressure specification section has 2 options: specify reactor pressure and calculate reactor pressure. The specify reactor pressure allows us to set the reactor pressure, which can be modified by unit procedure. The calculate reactor pressure calculates the reactor pressure based on temperature and pot volume. Specify the pressure specification as specify reactor pressure and set the reactor pressure to 1 atmosphere. The Streams tab allows us to specify the inlet and outlet flows as well as the time for charge and discharge operations. The batch cycle time is equal to the sum of the feed time, the operating time, the discharge time, and the downtime. We have a choice to either specify a batch charge or batch feed time. We will charge our BatchOp unit with acetic anhydride for 1 hour, allow 1 hour for discharge, and assume no downtime. Specify the reaction and crystallization by navigating to the Reactions folder in the navigation pane. Specify the first reaction by clicking New in the Reactions folder and specify the type as General. In the Configuration tab, click New to add a reaction. Specify the reactants as acetic anhydride and salicylic acid with a coefficient of -1 for both reactants, and specify the production as aspirin and acetic acid with a coefficient of 1 for both products. Go to the Kinetics tab and enter the specifications for the kinetic factor. Enter a kinetic coefficient value of 0.005, an activation energy of 20 kcal per mole, and a reference temperature of 60 degrees Celsius. Our reaction is first order with respect to each reactant. We can model this by specifying the driving force and providing an exponent value of 1 for both reactants. Specify the crystallization by clicking New in the Reactions folder, and specify the type as crystal. In the Crystallization tab, click New to create a new crystallization stoichiometry. Specify the reacting phase as liquid, solute as dissolved aspirin, salt as solid aspirin, and specify the reactant as dissolved aspirin. The Solubility tab allows us to choose from 3 solubility calculation methods: solubility data, solubility function, and chemistry. The chemistry method calculates the solubility from chemistry correlations. These correlations can be found in the Properties Environment Chemistry folder. We have 4 different options of specifying the chemistry: specify reactions, specify inert components, specify reactive components, and all components are reactive. Let's specify chemistry as our solubility calculation method. On the Kinetics tab, we must specify the crystal growth equation for all crystallization process specified in the Crystallization tab. We also have the option to consider nucleation and dissolution for each crystallization process. We will specify the crystal growth rate constant and the nucleation rate constant for our crystallization process. In the navigation pane, access the BatchOp unit by going to Block, B1, Kinetics. Here, we can define our reaction and crystallization for our BatchOp unit. Now, we can specify our unit procedure and run the simulation. We will supply 500 kilograms of salicylic acid for 0.2 hours. Heat the reactor to 75 degrees Celsius over an hour to allow reaction, and cool down the reactor back to 25 degrees Celsius over an hour to allow crystallization. To monitor the reactor contents over time, we can view plots available for our BatchOp unit in the BatchOp block, Home ribbon, Plot group. Here, we can view predefined plots available during simulation run. We can view the behavior of temperature, pressure, composition, duty, reaction rates, particle properties, and particle size distribution. Let's check our reactor composition as well as our particle size distribution. Our composition plot and particle size distribution plot updates as the simulation solves. We can see the effects of our unit procedures in our composition plot and particle size distribution plot. Around 0.2 hours in, we see our salicylic acid feed ending. Around the same time, we can see competition between reaction and crystallization. At about 0.75 hours, our particle size distribution comes to a halt since we are no longer producing solid aspirin. After 1.2 hours, we decrease our reactor temperature from 75 degrees Celsius back to 25 degrees Celsius. We can see the effects of decreasing our temperature at the 1.5 hour mark, where our concentration of aspirin in solution decreases as our concentration of solid aspirin increases. After 1.65 hours, our particle size distribution changes slowly as we produce more solid aspirin by reducing our temperature.